Morning.
Yeah, good morning. Can you hear me?
Yes, I do.
Okay, great.
Can you hear me?
So I'll test, can I test my screen sharing?
Yes.
Okay, this one. Okay, is it okay?
Yes.
Okay, great.
And I see the pointer too.
Sorry.
I can see your pointer too, just in case
Okay,
you will need it during the presentation.
Yeah, okay, it's normal. Okay. So then I'll start my presentation. Is it okay? Or yeah, maybe we can wait for all of the people are gathering. Yeah. Okay.
Yeah. Let's wait a bit. Usually we start a little bit later just to.
Yeah, sure.
Where are you now, in Tokyo?
Yes, I'm in Tokyo. So now in Tokyo is 5 p.m.
Okay.
Yeah. Actually, yeah. Thank you for inviting me.
It's
yeah.
weekly journal club.
Sorry.
Yeah, so we have let's say a weekly journal club, and we try to invite as many interesting, let's say, presenters as possible.
Oh, that's great. Yeah. And yeah, actually, so how to say? Yeah, thank you for finding our paper, since we haven't how to say, our paper have not been accepted to the journal while we are submitting now. So yeah, just
I guess it can take some time. Where are you? Which journal are you planning to submit to?
Yeah, we are already submitted to physical review A.
Okay.
So it's targeted to the quantum information or some like quantum computing field. Actually, the very similar method to our method is already uploaded to the how to say, accepted to physical review X Quantum. But yeah, actually we found we proposed our method independent of them. So yeah, I hope you can see both of our work. Yeah.
Publish, yeah. Yes, so I would say we already have a quorum of people connected, so I would say we can start. So today we have Bo Yang, who is gonna talk about quantum readout error mitigation. And so we are looking forward to your talk. Please, Bo.
Yeah, thank you. Thank you for introduction. So yeah, actually, yeah, it's a great honor to be here. So, and yeah, thank you again for inviting me to speak here today. So yeah, this paper, actually our work is presented once or twice in international conference last year, but we have just published our work on arXiv last month. Sorry, in January. So yeah, and let me introduce the collaborator of this research. So Dr. Rudy Raymond is a researcher at IBM Research Tokyo, and Dr. Shunpei Uno is a researcher at Mizuho Research. That Mizuho is one of the largest bank company in Japan, and also both of them are the members of KO Quantum Computing Center, while I'm a PhD candidate at the Department of Computer Science at University of Tokyo. So let's start. First of all, in short, this work provided an efficient quantum readout error mitigation framework, which can mitigate the 65 qubit GHZ states in 5 seconds in our normal personal computer. So this method is suitable for mitigating the measurement result with few dominant state labels. And actually, this has many practical use cases, such as device benchmarking, where we show the 29 qubit genuine multiplied entanglement on IBM Quantum devices, and also the modified Grover algorithms, which is more likely to be realized in near future than the traditional Grover search algorithm. So yeah, and also our code is available in GitHub. And of course, for the background of this work, we are now witnessing many kinds of quantum hardwares and some claims that the quantum advantage is achieved. So in addition, the quantum devices are already available online, and many softwares are also developed. And in particular, I stopped the screen sharing. Let me share again.
Yeah, no problem.
Oh no. Maybe my the PowerPoint is crashed. So I may take several minutes. Okay, so
is it alive?
Yeah. Okay, it's recovered. Can I see the? Can you see the screen?
Yes.
Okay, great. So maybe we'll start. Yeah, this one. Yeah, in particular, the size of IBM Quantum devices are doubled every year, and now the 129 qubit devices is released recently. So, but in current situation, many quantum algorithms and protocols are proposed, and such devices are available. These real devices are so noisy, as you know, that we cannot not use them for practical purpose itself. So therefore, to obtain a meaningful results from them, we have to combine some error mitigation techniques. And error mitigation plays one of the key roles in these parts. And the core scheme of quantum error mitigation is just like this figure. So in the presence of the noise, the probability distribution of the expectation value of observable is shifted from yeah, from the ideal one to noisy one. And we use the quantum error mitigation, QREM. Then we can make the probability distribution centered around, while there's a drawback that the variance is amplified like in this way. And we need more samples to achieve the same accuracy as the one before the QREM. So yeah, this sampling cost will grow in exponential scale in many cases, and yeah, actually, so far many types of quantum error mitigation are proposed. Yeah, well, some techniques like, for example, dynamic decoupling are used in the circuit construction part. So here we focus on the quantum readout error mitigation. So so the quantum error readout error mitigation, so we often call QREM, aims to mitigate the mitigation error in the outcome probability vector. Probability vector, or like distribution. So so measurement error is one of the dominant error in the current near-term device, with around 2 to 3% on IBM Quantum devices. So it is important to mitigate the readout error. So, but fortunately, this readout error can be characterized by a stochastic matrix called calibration matrix here, or assignment matrix. And this matrix is created through the quantum detector tomography, which investigates the transition probability from each single quantum states to other quantum states. So, and then once we know the noise model, we can just apply the inverse of the matrix to the noisy probability distribution. And this is the standard way of the QREM process. And yeah, this process, this standard algorithm is implemented as a library of Qiskit and widely used so far. But however, this noise characterization matrix has exponential size to the number of qubits on classical computer. So it makes the quantum readout error mitigation process highly inefficient. So it is infeasible to apply this standard methods to the measurement outcomes from those quantum devices with over 100 qubits, or even the mitigation with the around size of around 20 qubits is hard enough. So therefore, we have to design efficient methods, and this is our core motivation. So again, here we assume the measurement process is a stochastic matrix, which applies to ideal quantum output to output the noisy probability distribution. So then the quantum readout error mitigation process is like given a calibration matrix and a noisy probability distribution, then we want to either mitigate the obtain the mitigated distribution itself, or obtain the mitigated expectation value. So for the QREM, for the expectation value, many researchers gives efficient ways under various noise models. But on the other hand, for the QREM, for probability distribution, only a few previous work exist to the best of our knowledge. So now we'll we'll compare mainly compare these two previous works with our method. So one is the methods by Mooney et al. And the other is the methods by Nation et al. And all of these methods were proposed last year. And Mooney et al's method is the we can say it is the fastest among all of these methods, but its computational complexity is unbounded and the accuracy is relatively low. So, but for the Nation et al.'s method, this method is actually available through the Qiskit package called M3. So, and the idea of our method and their methods, these methods are quite similar, but we designed our methods independent of M3. So, yeah, and we have posted our idea already in last year's September, and their paper was published in in the same time period, and so actually their method is fast, as fast as our method, but they have several drawbacks in the error mitigation error part, and it is approximated, but not but will not output the exact mitigation error. And also we will later see our methods will give better performance on some important applications. Yes. So okay, and okay, this one. Okay, then before explaining our methods, I will briefly talk about the tensor product noise model, since all of these methods are based on the tensor product noise model. And here, recall the complete calibration matrix with exponential size in this form. We have to get this matrix by the exponential number of measurements, and also we have to store this matrix on classical computer using the exponential large computational memory. So it is highly inefficient, but fortunately, maybe maybe the PC the PowerPoint crashes, and then it breaks some materials in this slide, but I will still continue my presentation. And actually, when we assume that the noise is local to each qubit, or in the local qubit blocks, then we can write this construct this big matrix by the tensor product of a small local calibration matrix. Then by the measurement grouping technique, the measurement cost decrease from 2 to n to 2 to k, where the K is the largest size of the local blocks. And also the classical memory is, also becomes the efficient from 4 to n to n times 2 to k. Yeah, and this tensor product noise model is justified on IBM Quantum devices and used in many other QREM frameworks. Yeah, and for the justification of this model on IBM Quantum devices, you can see the experiments by Muni et al. This paper is the same as the previous method, QREM method of yeah, this paper. Okay, and so then we can move into the proposed method. So the proposed method consists of 3 steps. First, we apply the efficient matrix inversion to compute the roughly compute the mitigated vector, the frequency distribution, and then it might not satisfy the proper the criteria of the condition of proper probability distribution that where the vector should satisfy all the elements of the vector is non-negative, and also the sum of the elements is equal to 1. So in the step 2 and step 3, we deal with these conditions respectively. And in the step 2, we try 2 approaches. Yeah. So for the step 1, we the idea so is very simple. So we only use the trace of how to say, we only trace the probability of non-zero elements in the noisy probability distribution. So in many cases of the quantum computing, we will finally get the output with only few states with dominant probability, and when the state preparation error and the readout error is relatively small, the erroneous states distribute within small will distribute within a small Hamming distance from the non-zero elements of and the ideal outputs of the probability distribution. So, and this fact is also checked for IBM Quantum devices in Nation et al.'s work. So here,
sorry to
yeah.
interrupt. What is the Hamming distance?
Yes, I will explain in this figure. So here we only consider the non-zero elements, right, of the probability distribution, but we can also consider the how to say the state labels with a small Hamming distance. When we focus on the quantum states 1, 0, 1, 0, then the Hamming distance 1, the states with Hamming distance 1 from this state will be 1, 0, 0, 0, 0, 0, 1, 0, and 1, 0, 1, 1, also, and also 1, 1, 1, 0. Like this. This is the what I mean by Hamming distance.
Okay, so the states that I can reach with just 1 qubit flip, let's say.
Yes, yes.
Okay, thanks.
Okay, thank you. So yeah, and so using this assumption, we can greatly reduce the space of the computational space. And here, each element of the inverse of A, calibration matrix A, can be efficiently computed as in this form. And this form only takes the how to say, order n time to the size of qubits. For example, for this red pixel, this element can be computed by the product of this element of the calibration block and this element of calibration block and this element like this. So using this efficiently computable inverse matrix, and but yeah, so okay, and also by restricting the computational space into S, we write the subscript S like this to stress the vector or the matrix is restricted to the subspace S. Then we can each element of the frequency distribution here XS is computed by this form. So this takes only order n times S time. Here, this part takes n times, and this part takes S time. So ns time. And also, we have to, since we compute all the elements of the XS, then the total time becomes order ns square. And actually, if we only compute this XS vector, then the memory only order S memory is enough for this process. And so what, of course, as I said, mentioned before, S can be extended to the subspace with Hamming distance d from this subspace S. So, and the mitigation error can be bounded by the one norm of one norm M of the reduced inverse matrix A, this one, and the short counts. So this is used a discussion in the appendix of the other efficient quantum error mitigation process called CTMP by Brady et al. So next is that I will mention the difference between the Nation et al.'s method and our method. So actually, they firstly reduce the calibration matrix A into the small small subspace, and then with a renormalized process, then they inverse this matrix. But in our method, we firstly inverse. So how to say? We compute the inverse of the matrix A from the first, and just compute the elements of the reduced subspace S. This is the difference, but it is quite similar. So this is the first one, and sorry, the step one, and next is the step two. So in the step two, we are going to find the frequency distribution with sum to 1 condition. And for the first approach of this step two, we try to directly modify the vector by adding the small correction vector delta. And we firstly form the optimization problem in this way. And here, for the calibration matrix A, we decompose this calibration matrix A by SVD, singular value decomposition. And this process is efficient because A is a tensor product of small fraction of small calibration matrix, and it's we can compute the this efficiently compute the singular value and singular vector of the big calibration matrix A efficiently from those SVD of small calibration matrix. And then this optimization problem is converted to this form, and this form can be solved analytically by Lagrange multiplier, and then the answer becomes in this form. But it is still infeasible because we are computing the computational space is also in the 2 to n size. So we also reduce the computational space to S, and add some approximation. Then we get this form. Finally, get this form. So one bad thing is that the sum of the vector may not become exactly 1 here, but the computational space is computational complexity is become efficient. But in the next approach, the approach 2, we will finally obtain the corrected vector XS hat with the sum to 1 condition, exactly satisfying this sum to 1 condition. So yeah, the second idea is that solve the least norm problem to find the nearest vector. And actually, we recommend this this method in the real case application. So, and yeah, actually, this method is the idea is very simple also, and we convert this problem to a simple least norm problem, and then using the analytical solution, this one of the least norm problem, we finally obtain the correction vector Z, where Z can be denoted in this way. So, so here the correction vector, to compute the correction vector, we only have to only compute this part, the trace of the inner product of XS, so that which is roughly mitigated vector. So we only take this part only takes S time. Okay, so when we obtain the how to say feasible XS hat, then finally we have to cancel the negative elements in the XS hat to obtain the positive vector XS tilde. So in this process, there is already a great efficient algorithm by Smalling, Gambett, and Smith, and this the idea of their method is to put the negative how to say the negative value of the in the vector to the how to say divide the negative part and distribute them to the positive part. So actually this process can be implemented using priority queue, and we obtain the S log S time algorithm to the size S of the subspace S. So in total, the most time-consuming part is the step 1 with order ns square time. So this is the bottleneck. Okay. So next I will explain the experiments using these QREM methods. So do you have any questions so far?
Yeah, I may just ask what are the axes of the figures in the previous slide?
Oh, sorry. Okay, this one. This one,
Yeah.
right?
Yeah.
Okay. So are you asking about the
Yeah.
specific process of this?
Yes. What's
Okay.
on the y and x axis?
Okay. They solved the similar Lagrange multiplier problem, optimization problem, to obtain this protocol. But how to say, intuitively, they firstly they see the they sort all the elements in the input vector x s hat with negative values in this form, and they sum up the negative value to here, like mu5, and see whether mu4 can when mu4 is added to mu5 becomes positive or not. Sorry. In other words, they see when mu4 when mu5 is subtracted from mu4, whether mu4 is still positive or not. If not positive, okay, then mu4 is absorbed in mu5, and mu5 becomes how to say, more positive. And then once we find the value that, how to say, the elements that can totally cancel out this negative summation part, then we divide this negative value into equally small parts, and then so distribute the small negative factor to equally to the other positive elements. This is the whole process.
Okay, thanks.
Okay, thank you. So yeah, so we did 3 experiments. One is expectation value of GSD state on IBM Quantum Brooklyn. Next is the fidelity of GSD states, and the third is the numerical simulation of modified global algorithm. So we will firstly take a look into these 2 experiments on IBM Quantum Brooklyn. So we use the IBM Quantum Brooklyn device with 65 qubits and with a Hummingbird R2 core, which can achieve quantum volume 32. And we did these experiments this year. Actually, the condition of IBM Quantum devices will change a lot day by day. So yeah, I have to write these experiments, data of the experiments. And so for the setting of quantum readout error mitigation process, we use the Nation et al.'s methods, the implementation of their methods from their how to say, published library, Qiskit library called M3, and there's no open public resource for Mooney et al.'s method, so we implement their methods, and of course our proposed method and rigorous matrix inversion methods by our own, and this can be this is available in this link. And we, as I said, I did quantum readout error mitigation in MacBook Pro, a standard, how to say, personal computer. And the result is stored in this link. So for the construction of GSD states, so GSD states can be efficiently implemented in the on the real quantum devices with restriction of qubit connection. Because GSD states, how to say, it is enough to find a shallow tree structure with small radius. Yeah, and the depth of the circuit can be bounded on the square root n of the system size. And actually, I give proof of this bound, and yeah. So hope you can get access to my other paper. And yeah, actually, if we want to make 4 GSD state on the 65 quantum device, we can construct the quantum circuits in this way. So yeah, the first result is the expectation value of GSD state, and here we computed the expectation value under the computational basis. This experiment is also checked by the Nation et al.'s experiments, and we want to compare the proposed method and the Nation et al.'s results. So we can see the and also the way of the to compute the expectation value. There are 2 ways of the computation of expectation value. One is this, and the other is this way. And so here we can see the expectation value will decrease through the increase of number of qubits, and actually the mitigation error, how to say, mitigation error will increase through the the increase of the number of qubits. But since Nation et al.'s M3 package can only approximate their the mitigation error bound, so their outputs their output will not reflect the actual large error bound, but it becomes like small value. On the other hand, we can compute the exact error bound of the mitigation process. So yeah, this is we argue the same parts. And sorry, maybe the time is limited, so I will speed up my talk. So yeah, actually, when we see the mitigation time, we can see the rigorous tensor method scales exponential to the number of qubits, but the proposed method can perform the mitigation on on to the 42 qubit JT state in within 1 second, and 65 state in within 5 seconds. Well, M3 package also mitigate the 42 qubit JT state in very short time, but they use a much powerful computer. So the next is the fidelity of GHD states. So we check the genuine multipartite entanglement by checking the fidelity of GHD state with multiple quantum coherence in this way. So yeah, so time is limited, so I will not deep into this the process of this part. I will just show the results. So the fidelity of the GHD state was examined up to size 39 on CT5 quantum device. And you can see, okay, the x-axis is the number of qubits and the y-axis is fidelity. So when the fidelity is over 0.5, then we can say the state has genuine multipartite entanglement, and you can see without quantum error mitigation, so only 17 qubits is the maximum record, but with a proposed method, the score is increased up to 29 qubits size, and this this yellow line, it represents the result of our method, and you can see the purple. This yellow line overlaps the rigorous matrix inversion line, colored purple here. Then we can conclude that the proposed method is has the closest plots to the plots by rigorous matrix inversion compared to other mitigation framework. So this result is can be seen as a new milestone of device benchmarking of IBM Quantum experience. So so the Mooney et al. Used their own quantum error mitigation methods to show the genuine multipartite entanglement up to 29 qubits. But if we admit their methods, then we can achieve the 34 qubits genuine multipartite entanglement. But it is too big because their method did not follow the rigorous inversion plots, and so it is more reliable. So our method, the results is more reliable. Okay, so the last is the maximum likelihood amplitude estimation with modified global iteration. So I will call that the modified global algorithm, but this method, in short, this method avoid the use of phase estimation and use the shallower circuits and less CNOT gates. So therefore, this method has the is more likely to be realized in near future than the standard global search. And the advantage can how to say, the advantage high speed high convergence rate compared to the classical counterpart. So this classical counterpart scales only the square root of the number of global iterator, but using the maximally likelihood amplitude estimation, we can achieve the linear rate speed of the convergence rate. So yeah, the modified global iterator is the some variant of the MLAE, and they measure all 0 states, and thus it is suitable for the proposed to apply the proposed methods. And we did the numerical simulation by adding the measurement noise on the noisy simulator, and then apply our quantum readout error mitigation. So so I will directly show the results here. You can see the convergence rate of the this is the the left figure represents the readout noise with 0.01, and the center is 0.03, and the right figure shows represents the result under the readout error of 0.05. So here you can see the theoretical convergence line. It's a lower bound of the error. Is this red line, but so the Nation et al.'s method M3, the result of M3 did not converge at all, and for the larger errors, the raw results will not converge as well. But when applying the rigorous tensor rigorous matrix inversion, then we can see the quantum error mitigation recover the convergence original convergence rate, and our method is just on the plots of the rigorous tensor, meaning the proposed method output the smallest gap from such a rigorous plots. So actually, I'm sorry for hurry in last 10 minutes, but let me summarize my talk. That in this paper, we propose a time and memory efficient quantum readout error mitigation, and this error mitigation method has a possibility of to mitigate the measurement result from hundreds of qubits efficiently, and it has many applications supported by several experiments, such as when and has a great impact, such as when we achieving the 29 qubit GME on IBM Quantum device, then we can conclude that we have obtained a new milestone of the benchmark marking of the real device. And then since actually the modified global algorithm is originally resilient to the depolarizing noise, but through this previous numerical simulation, we can also say that the modified global algorithm is also resilient to the readout of noise. And actually, we have also applied the proposed method to other use case, such as the quantum correlation of the multiplied Bell inequality scenario, and we also found it is useful also in that case. So yeah, I hope yeah, the proposed method is used by many people, and yeah, it helps them. So yeah, thank you very much.
Thanks. Thanks a lot for your talk.
Yeah.
Let's see if we have questions. In the meantime, I may ask a question that is, so at the very beginning, you assumed this tensor noise, right?
Yes.
How, I'm not an expert in, let's say, Readout. How realistic is that the noise in the Readout is just local?
So are you asking about the this? Is this assumption
Yeah, how strong
justified or not?
is it? Yeah.
Yes. At least on the IBM Quantum devices, this holds, but I don't know in other devices. But actually, the tensor product noise model is also used in in other previous research like Bravi et al.'s work, CTMP, error mitigation framework, and other also Vandenberg's and Hicks et al.'s works. And yeah, at least we can ignore the since the 2-qubit correlated error in the mitigation process can be ignored. But yeah, actually there exists some quantum error mitigation research protocols that takes such error into account. Like, for example, Bravi et al. Also considering the only the 2-qubit gate, 2-qubit measurement correlated errors in their mitigation framework. But yeah, most of the mitigation protocols are based on the tensor product noise model, and you can use that so far. Yeah. Does it make sense? Or
yeah. So I assume it makes a lot of sense, and you have less let's say correlated 2-qubit errors in the readout with respect to the errors you may have, let's say, when driving the qubits and experiencing crosstalk and so on. So I'm not an expert, so I was just asking out of curiosity, let's say.
okay.
And
so actually, you can find this matrix is actually a situation of the real device, and you can see that the off diagonal part, it's very vague, but you can only see that this part and maybe this part, but yeah. And for the correlated, for the off diagonal part of the calibration matrix, which means that it is almost like tensor product of the small fraction of calibration matrix. Yeah. Sorry for interrupting. Yeah.
And so in the meantime, that if someone wants to ask some other question, I may ask you what's next. What are your follow-ups to this?
Okay. Well, one thing for the future work is to, actually we didn't analyze the error propagation, the propagation of mitigation error from step 1 to step 2 to step 3. So actually we have to analyze this part, but it is remaining for the future work. And for the future development, I guess this since the number of qubits is so getting larger, and next year will IBM says they will publish hundreds of the qubit, the device with hundreds of qubits. So in such case, I guess the proposed method will not work. So maybe because this proposed method has the time complexity of linear so scales linear to the to the size of qubit, but we use the square times of the computational space, which is almost equivalent to the short count. So when the short count increases, then this method becomes infeasible. So we have to think about how to say design a more efficient way. So that's my current interest.
Okay, so if we do not have further questions, we can thank the speaker again for his talk.
Yeah, thank you very much.
And yes, so we will see each other in 1 week again for the next Control Club talk. Thank you again, Bo.
Thank you very much. Yeah, I have really enjoyed this meeting. Yeah, thank you.
Bye-bye.
Bye.